Assalamualaikum warahmatullahi wabarakatuh, and have a good day. Today I want to talk about second law of thermodynamics. Do you know what's mean of the second law of thermodynamics? No. Okay. Second law of thermodynamics is defined as heat always flow from hot to the cool object. This such as when we have a hot water and a cool ice, we can put together, and the hot water energy will transfer to the ice or cool object. Next, extension, when energy is converted, some energy is lost as heat. This means when have a energy and energy is converted, so the lost energy that when we convert is called heat. Okay. For the formula is work in is equal to work up plus heat, or we can call it heat loss, and work in is greater than work out. Okay. For the next point, the second law of thermodynamics occur in certain direction, not in any direction. So this means from the, such as example, from the hot temperature to the cool temperature. Okay. For other examples such as a hot tea, a cup of hot tea does not get hotter in a cooler room. When hot tea in a cooler room, it will produce or release heat. Next example is the wire. Transferring heat to the wire will not generate electricity. When the electricity go through, and some heat loss will produce. And for the last example is transferring heat to the pedal wheel will not cause it to rotate. So the heat will transfer to the rotate machine. Okay. That's all from me. Thank you. Next, I want to talk about quality energy. Quality energy is related to how much work we can get out of the energy. Okay. As we can see this whiteboard, when the increased temperature energy can produce, so more work we can produce. More work. Okay. Then I want to talk to you about reservoir. Reservoir have two types: heat source and heat sink. For the heat source, we can see that heat source is supply heat, and for the heat sink is absorb heat. These two types has their own characteristic. For the example, I can show you that this, such as this material. This is a boiler, and this is a condenser. Okay. This boiler will absorb heat, and we can go for the energy source. And for the condenser, the heat will release. This type of condenser is for the heat sink, and this boiler is for heat source. These two types of the reservoir. through to the heat engine. Heat engine is the thermodynamic system operating in a thermodynamic cycle which net heat is transferred and from which net work is delivered. The second point is heat engine is any device that convert heat energy to the useful work. So convert heat energy to useful work. Then we go to the example. For the first example is work can be converted to the heat directly and completely. So it can have a work can be converted directly and completely. And the second, there is no work. So the converting heat to work require heat energy or heat engine. So it requires heat. And for this, it releases heat. Converting heat to work require heat engine. Okay, let's go to the schematic of the heat engine. For the schematic of heat engine, we have high temperature and then heat engine, low temperature and work. This schematic of the heat engine, I will explain to you. Firstly, they receive heat from the high temperature. So heat engine will receive heat from the high temperature, and they convert part of this heat to the work. Convert part to the work. And they reject the remaining waste heat to a low temperature. So the lost heat or released heat will reject to the low temperature. Low temperature also we can call the sink. And last, they operate the cycle. Okay, we look to the example of heat engine, or we can call the steam power plant. Okay. Firstly, the work will in at the pump, and it go through, it will go in a clockwise motion, and we find the boiler, and at the boiler, the heat will absorb or energy source from the furnace. Heat is absorbed, in, and after that, it will go to the turbine, and at the turbine, the work is produced, or we can call the work out. Work out, and after After that, it will go to the condenser. At the condenser, the heat will release. We can call Q out or to the atmosphere. After that, it will go to the pump and round. Okay. For the formula of this steam power plant is W net equal to W out minus W in, or Q net is equal to Q in minus Q out, or Q minus W equal to delta U. Delta U will be crossed if delta U will become 0 for the cycle. Okay. Next, we go to the thermal efficiency. Thermal efficiency is to measure the performance of the heat engine. Okay. The formula of the thermal efficiency is, firstly, is the performance. Performance equal to desired output over required output. And next is the thermal efficiency. Thermal efficiency, we can put the symbol NH equal is net work output over total heat input. And the formula is W net or out is over Q in. We can derive it such as Q in minus Q out over Q in. 1 minus Q out over Q in. If we beside other formula for this is 1 minus QL over QH. After we go through the thermal efficiency and we look at the refrigerator and heat pump. Refrigerator and heat pump is absorb heat from the low temperature, medium, and reject it to the high temperature. So we can see at this figure. Firstly, the evaporator. So heat will absorb to the evaporator, or we call QL. It absorbed from the refrigerated space. Then it will flow to the compressor. At the compressor, they leave the compressor with the high temperature. Then it will go to the condenser. At the condenser, the heat will reject or move out, and we can call it QH. Heat will reject to the surrounding medium. After that, the condenser to the expansion valve will flow with capillary tube to the expansion valve. And at the expansion valve, temperature drop to throttling effect. Temperature drop. Let's go to the schematic for the heat pump. Schematic for the heat pump have warm environment, heat pump, refrigerator, space at TL and the work. For the schematic of the heat pump, the cool refrigerated space at a lower temperature will move to the heat pump, and this is a QL. After they move to the heat pump will go to the warm environment, and we call the QH. The work net will move from this to the heat pump. This is a required input. And for this one is desired input. That's all for the schematic of refrigerator and the heat pump. Then we go to the coefficient of performance, or we can call it COP. Okay. For the refrigerator, coefficient of performance is equal to the QL over job work, or W net. For the schematic, it will occur at the cool refrigerated space at TL. Okay. For the heat pump, the COP, or coefficient of performance, is equal to the QH over work, or QH equal to QH minus QL. For the schematic, it occurs at the warm environment. Warm environment is TH higher than TL. Assalamualaikum, and let's look to the example first. For this example we see the question: a household refrigerator with a COP, or with a coefficient of performance of 1.5 remove heat from the refrigerator space at a rate 60 kilojoules per minute. The question is, determine A. Electricity power consumed by refrigerator, and second question is B. The rate of the heat transfer for the kitchen. For the first of all, we must collect the data, or we must circle all the points that it have in the question. Okay. Second, to answer question A, we must do TH refrigerator, and the last one is TL and work in. So, and this is QL, or we can list down is 60 kilojoule per minute. For the question, we must use the solution. Question A, he give a COP, or coefficient of performance, is 1.5. So we use the formula that we learn. So the formula is COP refrigerated equal to QL over W net. Then we calculate 1.5 equal to 60 kilojoules per minute over work, and we can arrange that so the work will go up and 1.5 go down. So the answer that we get is W net is equal to 40 kilojoules per minute times 1 minute over 60 seconds. So the answer is 0.667 kilowatt. Okay. For the question B, we use the formula W net equal to QH minus QL. So we arrange this formula and we use the QH equal to W net plus QL. And then we know that W net and QL, and we put down 40 plus 60 kilojoules per minute, and we can get that QH is 100 kilojoules per minute. That's all for the example for answer for question A and question B. Next, we go through to the second law statement. They have two statements. One statement is Clausius, and second statement is Kelvin Planck. For the first is Clausius. This means it is impossible to transfer energy from a cooler to a hotter body without leaving an effect on surrounding. For this, Clausius require a heat pump or other device which need energy input. For the schematic is so the high temperature and refrigerator, and for the bottom is low temperature. Okay. So this one is QL, and for this one is QH. So there is no work in. Work in is 0. Okay. For the Kelvin Planck, the meaning is it is impossible to operate the thermodynamic cycle to produce work with only heat transfer from a single reservoir. So that means for the there is require both heat addition and heat rejection. So for the schematic is a thermal energy reservoir. And go to the heat engine and produce W net. If for QH is 100 kilowatt, so for the work it also will produce 100 kilowatt. For the Kelvin Planck, there is no QL. QL is 0. That's the difference between the Clausius and Kevin Planck. Next, we have done for the second law statement for Clausius and Kevin Planck, and we go to the irreversible and reversible process. For this, I want to explain to you how the reversible and irreversible meaning and how it happened. Okay. For this one, irreversible process. Irreversible process is the process which cannot reversible. This one. And reversible process is process which can be reversed without affecting the environment. Okay. For this, to answer, example friction pendulum versus static boundary work versus static heat transfer, and the last one occur by friction and heat transfer finite delta T, and how we want to connect them. So the answer for the friction pendulum versus static boundary work and heat transfer is an example for the reversible process. And for the irreversible process, it occurs by the friction and heat transfer. So that's all for the meaning of the irreversible and reversible process. Now we proceed to the Carnot cycle. Carnot cycle first proposed in 1824 by the French engineer named Syauqie Carnot. Syauqie Carnot. And a cycle that working a reversible process. Reversible process. Okay. Anyway, but they have a PV diagram. So the diagram function as a 0.1, 0.2, 0.3 and 0.4. The circle or the cycle is moving in a clockwise for the heat engine, and for the anti-clockwise is a refrigerator. Clockwise is a heat engine. So there is a QH and QF. Next, we proceed to the Carnot principle. The first principle of the Carnot is the efficiency of all reversible heat engine operating between the same two reservoirs are the same. And the second principle of the Carnot is efficiency of an irreversible heat engine is greater than is less than reversible. So there is two principles of Carnot and the PV diagram for the Carnot cycle. In addition, we have three types of the Carnot cycle, and for this presentation, I want to tell you how to calculate the coefficient of performance for heat engine, heat pump and refrigerator for the Carnot cycle. Okay. For the first one, I want to tell you about the heat engine. Okay. The thermal efficiency of any heat engine, reversible or irreversible, and this is the formula is equal to 1 minus QL over QH, or thermal efficiency of Carnot heat engine. We can use the formula of thermal efficiency equal to 1 minus TL over TH. Okay. Next, for the Carnot heat pump, the formula of coefficient of performance is equal to QH over QH minus QL. We can write it, or we can arrange it such as QH over QL over QH over QL minus 1, and it also always can become TH over TH minus TL and equal to TH over TL over TH over TL minus 1. And for the last one, for coefficient of performance for refrigerator, the formula is equal to QL over QH minus QL, and it will become 1 over QH over QL minus 1, and the other side is equal to TH over TH minus TL equal to 1 over TH over TL minus 1. So these are three formula for the coefficient of performance for heat engine, heat pump, and the last one is refrigerator. Thank you.